Chapter 4: Sample Design and Sampling Error. Introduction. The selection of the elements from a sampling frame to include a survey is a critical part of the survey process. A survey needs a well-developed questionnaire, highly trained and motivated interviewers, excellent field supervision and management, a data collection mode matched to the type of information to be collected, and a well-conceived editing plan. How the sample of a survey is obtained can make a difference. Random or chance selection means that all human influence, both known and unknown, is removed from the selection process. Essentially, in its simplest form, the kind of sample selection used in carefully designed surveys has three basic features: a list or combination of lists of elements in the population, chance or random selection of elements from the lists, some mechanism that assures the key subgroups of the population are represented in the sample. It is important to note that random selection alone does not guarantee that a given sample will be representative. When chance methods, such as tables of random numbers, are applied to all elements of the sampling frame, the samples are referred to as probability samples. Probability samples assign each element in the frame a known and a non-zero chance to be chosen. These probabilities do not need to be equal. If there is a systematic failure to observe some elements because of the sample design, this can lead to sampling bias in the survey statistics. Even when all frame elements have the same chance of selection, the same sample design can yield many different samples. They will produce estimates that vary. This variation is the basis of sampling variance of the sample statistics. We will use from time to time the word precision to denote the levels of variance. That is, if the sampling variance of a survey statistic is low, we will say it has high precision. The samples and estimates. Not all samples for surveys are selected using chance methods. Many surveys use haphazardly or purposefully selected samples. They have a shared weakness. There is no direct theoretical support for using them to describe the characteristics of the larger frame population. When probability selection methods are used, there is not one single sample that can be selected, but many. A sample realization is one set of frame elements selected using a specific sample design. Each sample design can yield many possible sample realizations. The number of possible realizations is a function of the number of units in the sample, the number in the frame, and the sample design. Each sample realization has a mean and a variance of the distribution of values of y in the sample realization. The sample mean is called y bar, which summarizes all of the different values of y on the sample elements, and the variance of yi's in the sample realization is labeled as s squared. Another term for the variance of the sampling distribution of the sample mean is the sampling variance of the mean, the square root of which is the standard error of the mean. When analysts want to estimate the frame population mean using the sample mean from a given sample survey, they employ the standard error to develop confidence limits for a given estimate. Confidence limits describe a level of confidence that the means from all the different sample realizations will lie within a certain distance of the full frame population mean. The notation used for the standard error is SE y bar. It is a square root of the sampling variance Vy, that is, SE of y bar equals the square root of V of y bar. In sampling for surveys, one additional measure appears in the consideration of sampling variability. The sampling fraction, F equals little n over big N, which is merely the fraction of units selected into the sample size of size little n from among all the n elements in the frame population. Summarizing the discussion thus far, we do surveys to discover properties of unknown distributions of variables that describe something in the frame population. Probability samples assign known, non-zero chance of selection to each frame elements. The extent of the error due to sampling is a function of four basic principles of the design. First, how large a sample of elements is selected. Then, what chances of selection into the sample different frame population elements have. Third, whether individual elements are drawn directly and independently or in groups called element or cluster samples. And lastly, whether the sample is designed to control the representation of key subpopulations in the sample, called stratification. Simple random sampling. Simple random sampling, or SRS, is often used as the basic design to which the sampling variance of statistics using other sample designs are compared. Simple random samples assign an equal probability of selection to each frame element, equal probability to all pairs of frame elements, equal probability to all triplets of frame elements, or etc. Sample designs assigning equal probabilities to all individual elements of a frame population are called EPSOM. For equal probability selection method. We compute the mean of the variable y as y bar equals 1 over n summation from 1 to n of yi. And the sampling variance of the mean can be estimated directly from one sample realization as the v of y bar equals 1 over f over n times s squared. The term 1 minus f is referred to as the finite population correction, or FPC. The finite population correction factor equals the proportion of frame elements not sampled, or 1 minus f, where f is a sampling fraction. When f is small, the FPC is close to 1, and v of y bar equals s squared over n. The sampling variance, the standard error of the mean, and the width of the confidence interval depend on just two factors: how variable the values of the yi's are across the sample elements and how large the sample is. However, for a proportion, the sampling variance of the mean for an SRS has a simpler form. The V of P, which equals 1 minus F over n minus 1, times P times 1 minus P. Here, the sampling variance of P depends not only on the FPC and the sample size, but also on the value of P itself. It is also important to keep in mind that surveys often ask respondents many questions, and many statistics can be computed from each survey. For a given sample size, the levels of precision of different statistics will vary. The single sample size chosen is often a compromise among issues such as how much the investigator is willing to spend for the survey, which statistics are most important for the investigator, and what levels of precision are obtained for them with different budget allocations. Section 4.4, Cluster Sampling. Cluster samples do not select frame elements directly, but groups of frame elements jointly. One way to construct frames at reasonable cost is to sample clusters of elements and then collect a list of elements only for the selected clusters. And when a sample cluster is selected and visited, it makes sense to interview or collect data from more than one element in each cluster, also to save costs. To compute the mean, we have y bar equals the summation of alpha from 1 to a times the summation of beta from 1 to b of y alpha beta over ab. The sampling variance is v of y bar equals 1 minus f over a times the s squared of a. This is where s squared of a is 1 over a minus 1 times the summation alpha equals 1 to a times y alpha bar minus y bar squared. D squared is referred to as the design effect, and it is a widely used tool in survey sampling in the determination of sample size and in summarizing the effect of how sampled clusters instead of elements. It is defined to be the ratio of the sampling variance for a statistic computed under the sample design, in this case, the V of y, divided by the sampling variance that would have been obtained from an SRS of exactly the same size, the V SYS of y bar. Cluster samples generally have increased sampling variance relative to element samples. It is a result of mean test scores varying across the classrooms. With test scores differences across classrooms, it also means that we have a tendency to have similarity or homogeneity of test scores within classrooms. The more variability between cluster means, the more relatively homogeneous the elements are within the clusters. One way to measure this clustering effect is with an interclass correlation among element values within a cluster averaged across clusters. This correlation measures the tendency for values of a variable within a cluster to be correlated among themselves relative to values outside the cluster. The intra-cluster homogeneity, denoted MH for rate of homogeneity, is almost always positive, greater than 0. The rho or ROH equals D squared minus 1 over B minus 1, where B is the subsample size. Subsampling within selected clusters. What are the gains of subsampling? The design effect for the sample mean goes down and the precision of the sample mean increases. Spreading a cluster sample over more clusters while keeping the overall number of sample elements fixed usually increases total costs. Changing our unit of sample selection from an element as an SRS to a cluster of elements reduces costs, but the cost reduction comes at the price of higher sampling variance for the lean or larger sample sizes to obtain the same sampling variance. The increase in sampling variance is measured by design effect. The sampling variance for a cluster sample mean is driven by the rate of homogeneity and how many elements are selected in each cluster. The stratification and stratified sampling. Probability sample designs can be made better with features to assure representation of population subgroups in the sample. Strata are mutually exclusive groups of elements on a sampling frame. Each frame element can be placed in a single stratum. In stratified sampling, independent selections are made from each stratum, one by one. Separate samples are drawn from each subgroup using the same selection procedure. To estimate population values such as a mean or proportion, the strata results must be combined. An estimate of the population mean or proportion can be computed in each stratum, and these combined across strata to give an estimate for the population. The combining method will depend on how the sample is divided up across the strata. The proportion and allocation to strata. Proportion allocation is identical to selecting the sample in each stratum with the same probabilities of selection, an equal probability selection method, or EPSOM. The mean equals the y of ST bar, which equals a summation from h equals 1 to capital H, W of H, y bar of H, equals the weighted sum of strata means. And we combine them for V of y ST. The sampling variance is the V of H bar, which equals 1 minus F of H over N of H times the S of H squared, which equals 1 over N of H minus 1 times the summation of I equals 1 to NH times YHI minus YH bar squared. And we combine them for V of YST bar equals the summation from H equals 1 to capital H of W of H squared times 1 minus F of H over N of H times S of H squared, where we weight each stratum's SRS variance by the square of the population proportion of WH. Thus, the design effect is D squared equals the V of Y bar of ST over the V SYS of Y bar. What can we do without frame information to use in stratification? Fortunately, there is no information case is quite rare in practice. There's also almost always some kind of information for each sample case that can be used to group population elements into groups that are going to be different with respect to the survey variables. The disproportionate allocation to strata. The name and allocation for a stratified sample is one of the many disproportionate allocations available. It requires that we know not only the WH for each stratum, but also either the standard deviations, SH equals square root of SH squared. The sample sizes are NH equals N times WHSH over the summation from H equals 1 to capital H of WHSH. The name and allocation can lead to a very large gains in precision over simple random sampling, and even over proportion allocation. However, there are several weaknesses to the method. For one, it does not necessarily work well for proportions. Second, name and allocations works well for one variable at a time. Disproportionate Allocation to strata without good information about the within stratum variances can be dangerous, leading to increases in overall standard errors. Stratified sampling can achieve the goal of obtaining a sample that is representative of the population for every possible sample that can be drawn, a goal that cannot be obtained through purely random selection. Systematic selection. Systematic selection is a simpler way to implement stratified sampling. The basic idea of systematic sampling is to select a sample by taking every kth element in the population, determine the population and sample size, and compute the sampling interval k as the ratio population to sample size. Then, choose a random number from 1 to k, take it, and select every kth element thereafter. Systematic sampling from an ordered list is sometimes termed implicitly stratified sampling because it gives approximately the equivalent of a stratified, proportionately allocated sample. Section 4.7, the complications in practice. In practice, clusters seldom contain the same number of elements. There is a selection technique that is often used to select clusters of unequal size. It sets up a design that selects a sample in multiple stages. The two-stage cluster designs with probabilities proportionate to size, or PPS. Probability proportionate to size, or PPS, addresses this problem by changing the first and second stage selection chances in such a way that when multiplied together, the probability is equal for every element, and the sample size is the same from one sample to the next. This kind of PPS procedure yields equal chance selection for elements, and it ends up with the same number of elements being chosen from each cluster. Thus, it achieves epsilon and fixed sample size. The multi-stage and other complex designs. Subsampling through multi-stages of selection is often used in situations in which a list of population elements is completely lacking. It is cost-effective. Multi-stage sampling occurs when doing area samples. In summary, there are 4 features of sample design on which samples vary. The first is the assignment of variable selection probabilities to different elements on the frame. If the higher selection probabilities are assigned to groups that exhibit larger variation on the survey variables, this reduces sample variance. If not, sampling variances can be increased with variable selection probabilities. Second, the use of stratification, which sorts the frame population into different groups that are then sampled separately. Like other things being equal, the use of stratification decreases the sampling variance of estimates. Third, the use of clustering, which samples groups of elements into the sample simultaneously. Other things being equal, clustering increases the sampling variance as a function of homogeneity when the clusters on the survey statistics. And lastly, the number of selected units on which sample statistics are computed. Other things being equal, the larger the number of units and the lower the sampling variance of statistics.